Good afternoon, everybody.
Afternoon,
Good
Prof.
afternoon.
Afternoon, Prof. How are you doing?
Good in yourself.
No, great stuff. I'm glad to see everybody logged on. And thank you so much for availing yourselves for this webinar. So we are slightly early. It gives us some time to have a bit of a chat so that we could be in a position to be better prepared for the webinar. I think the issue of the cameras, so when you're on the floor, it makes sense that your camera is actually on, but for the panelists, it will make sense that all of us, typically the cameras are on, but please feel free when you're not on the floor to switch it off if there happen with issues. We had structured the questions to you up front. So during the webinar itself, what would happen is we'd ask people to put any questions on the chat room, and we'll try and pull them from there just to create a bit of order, or else it could be all over the show. But when it comes to your slots of the panel, like when I'm speaking to the director or Mr. Lushozi directly, I'm gonna be asking the questions that we had given through to you. Your questions, Prof, they're a bit all over the show, so those will come from the floor. But the panelists themselves, please feel free to engage the Prof after his presentation. I think that would add a lot of value as well. We are just waiting for one panelist. I don't know if Jay is coming, Prof.
Well, he's aware of it, so should be. I'll just double check quickly with him.
Okay.
Please send him a message.
Because I know our IDC panelists had a bit of a challenge, and we struggled a bit. Dr. Kuzo, are you there with us? You know, your picture came late, so was not in the marketing material, but do feel free to show your face now. We won't bite.
I'll show my face just now, sir.
Okay. Thank you so much, though, for taking the time. I think it's a good webinar to be able to educate about the space and see if we can start making a difference.
Thank you.
Matlajo, how are you?
I'm good, and you, sir?
Thank you for coordinating everything. Truly appreciate it.
Okay. I'm just going to wait for one more panelist, and then I will let everyone in.
Okay, not a problem. So we'll hear from Jay, and then we can take it from there.
Yeah.
Okay.
Kulakani, Jay said that he just had an emergency, but he is rushing back to his place. He'll join later. So I'll start presenting, but he should join later as soon as he gets back at his computer.
Cool. No, thank you so much, Prof. Appreciate it.
That he also sent him the link.
I forwarded through to you, Prof. If you remember, and asked you to kindly forward it through.
I can't remember if I forwarded him the specific or the link, because I registered this morning, and obviously I sent it through to other people that I thought could join, but not necessarily the panelists. I thought that they would already have it. So let me just quickly go and.
But it was also sent to him via the secretariat. I'm just not sure if he received. Sometimes people pick things up when they are coming from an email they know and understand. That's why I was asking for that extra verification from your side.
Yeah. So what I'll do is I'll just quickly forward him this link as well.
Okay.
Kulegani?
Yes.
Can you see me now?
Oh, yeah. Doc, are you good?
I'm good, and yourself?
Great stuff. Are you enjoying Joburg water? Are you changing the world there?
Yeah, actually, it's very interesting. A bit of a challenge, but it's nice. I'm enjoying it.
Okay, Doc, great stuff. I see we've officially opened to connect to our webinar colleagues. So maybe we'll give it 5 minutes and then we can take it from there. Colleagues that have just joined, we just said we'll allow for 5 minutes and then we'll start at 5 past, just allowing people to connect. Thank you. Okay, colleagues, it's 5 past. I think it's only fair that we can start with the webinar. Everybody is welcome to this Conduit Hydropower webinar, and we are truly glad to have you here. A special welcome to the Easa president and the board members who have actually connected, and another special welcome to the panelists which are joining us today. So I'm just going to introduce them, and if they could kindly show their faces and be on camera when we go through them. We've got Prof. Van Dijk. He's going to be our keynote speaker today. He's a professor at UP, and furthermore, he's the head of water and sanitation at LTM. We have Mr. Lushozi. He is a program manager heading up growth and innovation at Rand Water. We have Dr. Kuzuayo. He heads up innovation in Joburg Water. Jay from Water Research Commission. Mr. Bagwan, he's running a bit late, so he's going to join us later. IDC apologized they had an emergency, so they won't be able to join us, but the questions that were fielded to them, they will circulate the answers, and then we can share with everybody who had joined the webinar. The prof, when he presents, please feel free to draft your questions on the chat room. I'm going to pick them up from the chat room and be able to relay them to him. If there are time limitations, all of the questions will still be answered even afterwards, so that all of the answers are taken through. The panelists were fielded with questions from the board, and they would be asked through those questions, and they'll give the answer. But if there are follow-up questions, please feel free to use the chat room. Conduit Hydropower is a massive opportunity, and with this webinar, we are looking forward to exploring the opportunities that exist, to exploring the case studies and some of the basic theoretical approaches that make them work. And without further ado, I'm going to give it to the prof to take us through the work he had prepared for the webinar. Prof, over to you.
Thank you so much, Kulakani. Just want to confirm that you can clearly hear me.
We can definitely hear you, Prof.
Great. I'll start sharing my screen now and start with this presentation. But first, just like to say thank you for the opportunity, and also thank you for pushing me up to a professor status. Let's just call that the prof at the moment stands for professional engineer and not yet for professor. That is still sort of in the making here at the university. They are a bit more reluctant to give me that title, so I'm still working on that. So, but thank you very much for this opportunity. So I'm going to share my screen. That one. I think I then need to just swap this around. So hopefully you can see the screen now in presentation mode. Is that right, Kulakani?
Yes, we can. We can.
Oh, great stuff. Let me just move this camera. I think it should be over here somewhere. Okay, so the title of today's presentation is on Conduit hydropower and the development of that. And we've got a number of panelists that's supporting this. And I am based at the University of Pretoria as well as at LTM Energy, heading the hydropower section there. So what I'll do is I'll firstly give you a bit of an introduction of what we can expect in this presentation of mine. It's probably going to be about 30 to 40 minutes in length. And then there's some opportunities for some questions, and obviously through the panelists as well. And I'll first start off with the objectives of this specific topic of mine, give you a bit of an introduction, some opportunities, just highlight those, then look at the different components. So that's where the theoretical academic component comes in. Look at the development process, the technologies that is out there that could be utilized. then touch on some examples, and I've only selected a few. We now have many more that can be discussed, but that will be a day webinar and not just an hour and a half webinar. And then some other examples as well. End off with the conclusion and then a take-home message that I've got for you on this. Okay, so firstly, objective is, when is it a viable hydropower project? So either minimum head or flow. Is it, do you look at internal rate of return? Do you look at payback period? So hopefully through this presentation, I'll touch on that. When would you consider it a viable hydropower project? The next thing is, what is the technology? What works and what does not work? And the application of that technology. When do you apply it and how do you apply it? And then through some of the case studies, hopefully educate and teach you something about what you need to think of when starting to develop a potential hydropower site like this. Hopefully through this as well, we'll stimulate the market engagement further, as well as engaging the finance sector for such developments to understand how this could possibly be financed, and what options you have. So that is the objectives. So just a small little video clip showing one way of utilizing the flow of water, and this is a kinetic hydropower installation and the use. And for these people, this is definitely a viable hydropower project. They're getting the meat cooked using the power of water. So in South Africa, we are the country with the second largest installed hydropower capacity in Africa, but we produce less than 5% of the total electricity is actually from hydropower. We've got some large pump storage schemes, so that pushes up this hydropower capacity, but we actually don't generate a lot of our electricity from hydropower. We don't have the many conventional hydropower opportunities as we have in the rest of Africa, simply because we're a water scarce country, but we do transfer large quantities of water daily under pressurized or gravity conditions over large distances and elevations. And this is done in canals or pipelines, tunnels, and so on. So there are opportunities at other existing water infrastructure, and we call them the so-called unconventional opportunities. So to generate hydropower, we need head, flow, and then the third thing is we actually need a use for the generated electricity. So here's just a video clip showing the typical installation that's required. It starts off with having an upper reservoir. From the upper reservoir, water is fed through a penstock down to a turbine room. Where it enters the turbine room, we open a valve, and that then allows the water to flow into a turbine. Once it flows into this turbine, we open the wicket gates, and that controls the flow, and it's guided onto a runner. It's called a runner in a turbine, not an impeller. That runner is connected to an axle. The axle turns a generator, and the generator then converts the mechanical energy into electricity. That electricity goes through a control panel, and eventually is fed back into, or fed into the grid, or it's just used on site if there's an application for that. The water that has gone through the turbine is then fed through a so-called tail race and into the downstream reservoir. So this is the basic principle of hydropower. So you saw the head difference between the upper and the lower reservoir. You saw that there was flow between the upper and the lower reservoir, and then there's a need for electricity. It's taken somewhere, either on site then, if it's smallish type of installations, or it's fed into the grid. So why hydropower? So we all know about the electricity shortages we've got. And just last week, we had some good examples of that again. We all know about the rising cost of electricity, which is making all of these renewables even more affordable. And the whole awareness and concerns we have with the environment creates a drive to the renewables and the greener type of technologies. We have a need to utilize all our available resources, and especially if it's a renewable resource that I'm sharing with you today, that actually proves that it can be a viable alternative in a number of cases. So the classification we've got for hydropower in South Africa is we classify it as pico when it's less than 20 kilowatts, micro if it's between 20 and 100 kilowatts, mini 100 kilowatt to 1,000 kilowatt, and small is 1 megawatt to 10 megawatt. After that becomes large, so the ones at Griep Dam and Van der Kloof Dam that Eskom has and Mbashe, that will be classified as large. So our focus here that we're looking at is in the whole spectrum from pico to small that could be evaluated for conduit hydropower. So where are the opportunities? So here you see a schematic of a network of rivers, canals, pipelines, which all has opportunities that could be looked at and developed. The conventional one would be at position number 1 there at the dam on the top. And this opportunity over here is a conventional storage dam with a releasing water into the river, and you generate electricity. And there are many of these examples throughout the world. Number 3 would be the pump storage schemes, and we've got a couple of those in South Africa. But then through the rest of the distribution network or canal systems or weirs and that we have in the country, we also have opportunities to generate some electricity. And conduit hydropower focuses on positions 4, 5, 6, 7, etc., where we have water in our existing pipeline networks, being it raw water or potable water, where we then have an opportunity to convert that pressure in the system to a hydroelectric power that we can generate from it. So we see these as some low-hanging fruit. And why we see it as low-hanging fruit is some of that infrastructure is already there. It's not, you don't need to build a new dam or construct a new penstock. It's already there. And all you need to do is latch onto that and add this subsequent benefit that you can actually get from the system by adding on a turbine. So some opportunities will be your typical, I've got a whole range of dams throughout the country, and it's actually unfortunate that we've got so many dams in the country. They sometimes call us the most dammed country, but we don't have that many hydropower installations at these dams, at these storage facilities. So just think of the water that's being released down the Vaal River. It has to be released for the environmental release. Why not just have a turbine on that release? So we're not saying let all the water from the Vaal Dam. We need it for obviously Gauteng. But if you have to release the water anyway for the downstream river system, why not just add your turbine to that? So that will be more the conventional one. So we're focusing it today on this presentation on the more unconventional ones. So in South Africa, we've got numerous municipalities, district and local. We have the Department of Water and Sanitation, Eskom, irrigation schemes, mining, and all of these entities have opportunities to add a hydropower plant to some of their pipelines, to the wastewater treatment works, to the water treatment works. And it is just a case where one needs to find that location where you've got the head and the flow, and see whether or not you can add a turbine instead of dissipating some of that energy with a valve. Why not just add a turbine to it and convert it to a renewable energy source? So just 3 examples in the city of Tshwane. There's many more examples in the city of Tshwane, but I just highlighted just 3 here, where we've got at 3 reservoirs, Heights, Garsfontein, and Klapperkop. We can generate small micro installations or mini installations, sorry, and with high internal rate of returns and quick payback periods, and the levelized cost of this electricity being probably less than half or probably a third of what the current levelized cost is of coal generated electricity. So and it makes sense to develop these, and the city of Tshwane has gone and developed some of these, which I'll share with you. So as I mentioned, what's needed, the components is you need a head difference and you need flow. So the head will depend on the pipe length and the diameter and where's your intake, where's the outlet, where's the powerhouse. So this will be the picture you see there is of a more conventional one where you might have had a water wheel situated next to it and they utilize this height difference there. So in our pipe systems, we look a little bit differently at it. We don't have this open flow of water. We have it in a sort of confined, closed conduit. And that's why we refer to it as Conduit hydropower. So that's the one component, is the head difference. The second component is the flow, and that could be variable as well, depending on, in most cases, we look at it in the hydrology sense. Does it rain enough? What does the catchment look like? What is the storage? But in Conduit hydropower, we don't look at the rainfall. It's not important for us. We're looking at what's flowing in the pipeline already. So there we look at demand patterns. So we look at more at the hydraulic side of things. What's the reservoir capacity? What's the system layout? And there's the formula. I'll get back to that now again, is power equals rho GQH multiplied by the efficiency. So I'll show it in an example for you in a second or so. So Conduit hydropower is similar to what I showed you in the video, where you have the upper reservoir and the lower reservoir. Conduit hydropower is from one storage reservoir to another storage reservoir. So these concrete structures you see in town, and we have water flowing under gravity from the reservoir number 1 to reservoir number 2. And the way we control flow in that pipe system is by choking it. We choke it through a so-called PRS, which is referred to as a pressure reducing station. And in that pressure reducing station, we have pressure reducing valves. Every one of you also have a pressure reducing valve at your house. It's where the water goes into your geyser, and we have the same type of valve there where we choke the flow and we control the pressure going into your geyser to only be 4 bar or 400 kPa or 40 meters of pressure. And the same then happens in our water distribution bulk water supply lines, is we have to control that water going into the end reservoir and to control the flow. So this pressure reducing valves, basically, as I mentioned, chokes the flow. And it's a mechanical device, but why do you want to throw away this pressure we have in the system if you could rather add a turbine in there and force that water to go through the turbine? If it goes to the turbine, it will start turning the runner. The runner turns the axle and it starts generating the electricity through the generator. And you get rid of that same amount of pressure that you wanted to get rid of, but now you force it through the turbine. So it's a very nice retrofit to existing systems where we have the pipeline, we will have the pressure reducing station, and we now have the turbine in parallel to that. So you would rather force the water then to go through the turbine instead of going through the valves. You would always need to have the valves because there might be a case where you want to service the turbine and then you still need to supply water. Remember, this is a subsequent benefit we're getting from the pipeline, and the main function is still to supply water. Very importantly, this operates 24 hours a day, 7 days a week, or 360 days annum. So I'm at a 360 because you might have a few days of maintenance on the pipeline that you're not going to be able to supply. So, but what I'd like to show or highlight is that you have it as a very continuous base load of electricity that can be generated here, and not just in the daylight hours or when the wind is blowing scenarios. We have here a very constant, very predictable type of electricity generation that we can get from this. So the development process would be identify the site. So that's the first step. Determine generation potential based on the flow and the head that you've got available. Consider some site layouts, the configurations that could work on that specific site. Consider the turbine options, and I'll show you some turbine options that can be considered. Then there's the application, or what you're going to do with electricity. Are you going to put it back into the grid, or are you going to utilize it on site, or are you going to use it as a mini grid standalone type of application? And then we also look at the economics of this. So there's a bit of a process, a scope of work that you go through to eventually develop a site. But the most important three elements is flow, head, and a use for the electricity. The rest are just technical information on how you're going to do it. But you need those different elements. So get back to the formula. The formula says rho GQH multiplied by the efficiency. So a very simple formula. It's very similar to a pump, but then in a pump, it's to use electricity or the electricity that it needs to drive it. There you would divide by efficiency. Here we multiply it by efficiency. The density of the fluid, in most cases, will be water. So it's 1,000. Gravitational acceleration is pretty fixed in South Africa, 9.81. So you can use that. The flow would be in cubic meters per second. So if I have 200 liters, for instance, that will be 0.2. The head would be the head that you could actually dissipate in meters. And then the efficiency. That varies between 50 and 85%, just depending on the type of turbine you use, the application, and so on. So for the smaller installations, we probably drop down to 60%. But for larger type, sort of more mini to small installation, we get close to 85, 87. The turbine actually is almost 90% efficient, but taking into account the generator as well, we probably drop down to about 85, 86% efficiency for a properly installed or properly designed turbine. So how do you go about determining then what power you can generate from it? Well, you can just take one of the selection graphs from a turbine manufacturer, take the head, on this case on the left-hand side, take the flow rate and the bottom axis. In this case, it was 100 meters of head and 200 liters a second of flow. And that you go up to where it intersects and you can read off that it's about 150 kilowatt. If you do the hand calculation, it's 1,000 times 9.81 times 0.2 times 100 times, let's assume the efficiency of this type of installation, maybe 0.75 or 75% efficient, gave me 1,470, sorry, 147,000 watts. So that's 147 kilowatts that can be generated using these parameters of 100 meters of pressure head and 0.2 meters of, 0.2 cubic meters a second of flow. As you can see, it's a direct relationship. So the power is directly proportional to the flow and directly proportional to the pressure head. It, however, is a lot better to have pressure head than flow. If you have a lot of flow, it means everything becomes a lot more bulky. You have to have bigger valves and bigger pipes, where with pressure head, you just have to have them a little bit stronger. So I would love to install installations in the Alps and in Drakensberg, where I've got lots of pressure head. But flow is also directly proportional to it, but it means your installation becomes a little bit bigger. So onto the technologies. So just to highlight, there are no proprietary technology. The technology we're going to use has been in existence for hundreds of years. We apply it in a little bit of a different way now in the Conduit hydropower environment, but it's not a special type of turbine. Yes, you get newer technologies that's coming out, and I'll show you some examples of that, but you don't have to have a technology that's only supplied by one supplier. So the grouping of turbines that we do get is basically grouped into two. So the one is a reaction turbine, and the second grouping is an impulse turbine. And the application is just very important. So if you see on the bottom left-hand, the picture there, the orange would be, let's say, the location of the turbine. So you would have the pipeline coming in from the left. It will go through the turbine. So you'll have pressure on the left-hand side that you'd like to dissipate. You'll have the turbine, but you can see on the right-hand side, you still have water and pressure and the pipeline. So that is pressure on both sides of the turbine, basically. The impulse turbine is water coming in from the left-hand side, going through the turbine, and then it's released to atmosphere. So there's no pressure on the downstream side. You can't have it submerged on the downstream side. It's open to atmosphere. So it's just two different ways, and I'll show you some video clips exactly of what that looks like and how this operates. So reaction turbines, pressure on the up and downstream side, and impulse turbine would be pressure on the upstream side, but atmospheric conditions on the downstream side. So immediately that should highlight the typical application for this. If I have a pipeline underground coming in and it feeds into a reservoir and the reservoir level is above ground level, then that means there's going to be pressure on the downstream side. That means I need to go for a reaction type turbine. If I, however, have a pipeline that goes up the reservoir side to the top of the reservoir and it discharges into the top of the reservoir, then I could go for an impulse type turbine because it discharges to atmospheric conditions on top of the reservoir. So it's just horses for courses, what would work. And then linked onto that would be the pressure range. And I'll show, when I show the different turbines, I'll talk about the different pressure ranges. So it's just important, reaction, we have this pressure on the downstream side, whereas with impulse turbines, we have it open to atmosphere. So this would be the conventional way or typical look of a Pelton type turbine. It's a little schematic on the left-hand side, generator, axle, the turbine, and you have your inflowing pipe. So this schematic only shows one pipe coming in, and then it discharges water through a very small nozzle, and that nozzle injects basically a high velocity stream of water onto the runner, and the runner are these little buckets you see are mounted around the axle, and that then forces this runner to start turning. On the picture on the left-hand side, the schematic, you only see one pipeline coming in, but in the picture on the top right-hand corner, you can actually see that you could have multiple jets ejecting and injecting, water onto the runner. That sometimes creates a better balance, and if you've got more water, so the turbine manufacturer will provide that information in terms of what would be the best sort of solution for your specific installation. So just showing a video clip of what this would look like. Sorry, go back. So the valve is opened and that starts forcing water onto the buckets at a high velocity, which then turns the runner. But as you can see, once it's hit those buckets, it just falls into the sort of downstream volute. And there's no pressure that you see in this little video. That's a Pelton, so this will be classified as an impulse type turbine. If we go to a Francis type turbine, this is usually when you see this sort of shaped, curvy type of turbine. And the reason we have this is to create an equal distribution of flow all around this turbine. And the water is then forced through that sort of casing, and water is then guided onto the runner, which in this picture on the bottom right-hand corner is the red part. So the red part would be the runner, and the yellow part there would be the wicket gates, which actually you can use as guides and forcing the water and the amount of water you'd like to guide onto the runner. So it gives you a bit of control over that. So we already saw a video, so I'll just play that last section again. So this example, this is a video we have from Conduit, which is a big turbine manufacturer in the world. This is a typical example of a Francis installation. And as you can see, there's pressure on the upstream side, as well as pressure in the tail race side up to the downstream side. So we have a pressurized, and this is a reaction type turbine where there's pressure on both sides. Another example would be a cross-flow turbine. This is again an impulse turbine. So if you look at this picture, water comes in from the left, it goes through this sort of drum-like runner and then is released to atmospheric conditions. And we've installed a few of these in South Africa now. So for impulse turbines, the first one, the Pelton, that will be more for the higher head type of application. So a lot of them installed in the high maintenance areas. We've got high head. Francis turbines can also handle high head, but they're sort of medium to high head. These cross flow, or another name for it is bunkie turbines, would be more the medium head, maybe 20 to 50, 60 meters of head that you can have from these type of installations. And then another technology which is very common would be the Kaplan type turbine. So So the Kaplan would be a propeller or that you have in the water. And this bottom picture on the schematic shows typically the S bend also that you get, where water would come in from the penstock and it will turn the Kaplan propeller, and there's a shaft going through the pipe wall and then onto the generator, and then the water is released with downstream. It's very common type of installation for low head installations. So maybe up to 30 or so meters of, and so huge volumes and low head type of installations, where the Pelton would be lower flow volumes, flow rates, but much higher heads. And then you get some newer type of technologies that are being introduced. So a turbinator is a type of Kaplan turbine that's connected to the dam, but sort of discharging the atmosphere to a certain extent. You get a siphon type turbine, and you get hydro engine is a new type of Pelton type, but sort of horizontal buckets that they've got. And then hydrodynamic screw in the bottom right corner would be like an Archimedes screw. So for low head installations, at maybe at waste it works, but hydrodynamic screw means it's sort of the inverse of Archimedes screw. So Archimedes screw for pumping water up, the hydrodynamic screw would be for releasing water and generating electricity from that. Some other unconventional ones would be, there was a company called Lucid Energy. I do not believe that they exist anymore, a few years ago, and they came up with the design of a spherical type turbine in large diameter pipelines. Was not a very efficient type of turbine, probably close to 50%, but it did allow for installation of this anywhere along the pipeline. And then probably not as unconventional, it is used quite often, would be pictures on the right hand side, and that will be pumps as turbines. So this is where you use a pump and you just use it in the wrong way. You turn it sort of not upside down, but the flow goes into the outlet and out of the inlet. So you just swap it around. Now, the impeller in this case obviously may need to be changed for this, but there are advantages of this, and that is that you get them, these pumps as turbines or the pumps themselves are a lot more common, a lot more modular, so it might be easier and off the shelf to obtain. But a negative, unfortunately, about this would be that they are not as efficient. And as I'll show just now with the cost estimates, that although you might have a saving on installing a pump as a turbine, so it's called a PAT, pump as turbine, in the long run, this might not be the best solution, as you would, as the capital pays off quite quickly on the project, then having a higher efficiency for the next 15 years is a lot better than having a cheaper initial capital layout for this. But it is used as a way of generating electricity as well. So part of the turbine component is one, and the generator then, but next part is what will you do with this electricity that you're generating? So one way is after you've generated it, would be the top part of this picture, is you have electric distribution board, and then from that you users, whatever users that would be. But unfortunately, you cannot change the flow going through the turbine very quickly. And if somebody then switches off a light or on a light, that means that there's going to be a demand change on the system. And your turbine is still generating the amount of power that whatever the flow and the pressure is. So what we usually then would have would be some regulating system that regulates the resistance and creates a constant load. So whatever I'm generating, whatever is being used by the users, whatever is left, I'm then dissipating that electricity. You can do that with water regulators, heating element, water dissipation of that, or just air dissipation for even smaller installations. But you can't just generate electricity and not use it, so you have to get rid of that. Otherwise, you're going to burn out the generator. Another option would be if you grid connected. So you have a turbine, the control panel, and then you feed it back into the grid. You could also feed users, but in this case, you are synchronizing your turbine to the grid. In the first installation, you have to balance that by adding the regulating system, where you don't have that need when you have a grid-tied type of system. And then decide on, if you have a grid-tied type of system, or even just own use, how are you going to manage that? Is it going to be through a wheeling agreement? Is it going to be for own use? What will be the best way of managing and handling that? So just again, talking about the regulators, that's more for the smaller type of applications. As I say, as soon as you go to larger installations, then you're probably going to have not enough demand on site, and then you put it back into the grid, have that grid tied. So let's go into some examples. The first example I'd like to show you is one we did for Bloem Water in Bloemfontein. So the picture you see here would be of water being purified in the bottom right corner at the Welberg Dam. It's pumped to the hook, and then it gravitates to Uitkyk Reservoir, and then it gravitates a further 40, 50 kilometers until it gets to Brandkop Reservoir, which then supplies Bloemfontein with water. And approximately 70% or so of Bloemfontein's water actually comes via this pipeline. The old 1.1 meter diameter pre-stressed concrete pipeline. So one of the critical things was to make sure that whatever we do on the system, we do not damage the pipeline. I don't want the turbine to suddenly shut down and then I get a pipe burst. The main function is to supply water. We are just taking off a subsequent benefit by generating electricity. So this pipeline actually has a number of opportunities. We can generate electricity at Uitkyk, and then it gravitates further until it gets to Brandkop Reservoir, and there we can generate some more electricity at that specific site. At each of these two installations, we probably have between 350 and 400 kilowatts we can generate, but we did this project a few years ago, and this is part of funding we obtained from the Water Research Commission, and we only then installed a smaller installation as initially a pilot, although they're using it at the moment. So what this looks like is just a plan view of this. Water comes in here to this dark blue arrow, and then in the past, it would have gone down the light blue arrow into the reservoir. There was a T-piece, and we installed onto that T-piece, we installed some pipe work, and we took off only a portion of the flow. The flow is about 1.1 cubic meter a second. We're only taking about 30% of that. We're sitting at about 300 liters a second that we're now taking through our offtake, and then it goes to the turbine inside this turbine room. After it's generated the electricity, we dump all of this water into the corner of the reservoir. So we haven't consumed any water. We just, instead of dissipating it through a number of pressure reducing valves, we are just doing that now through a turbine. And I'll show you a picture of that now. Cost-wise, we were probably at about 3.5 million rand, with the biggest portion being, in this case, the electrical connection in the Bloem Water office, but also the turbine we imported from Italy. In this case, it was an IRM cross-flow type turbine. And that was sort of the biggest two cost components. The turbine room itself was about 500,000 rand. And I'll show you an example where in another installation, we actually don't need a turbine room. So just to put it in perspective, that probably the biggest cost component would be the turbine. So this installation was opened in 2015, and this is a standalone installation. So it's not connected to the grid. The maximum power we generate there is 96 kilowatts. It utilizes about, I said, 350 liters a second. It's about a third of the flow to this reservoir. And there's the 40 meters of head that's available to do this with. The blue in the front is the turbine. The black part in the back is the generator. And then against the wall there in the background is all the regulators. In this case, we've got the regulators that dissipate the excess electricity with heating elements in the water. So the water, after it's gone through the turbine, if some electricity is not being used, it is dissipated with the heating elements we've got through water dissipation. It was launched in 2015, and this plant is not feeding into the grid. It feeds the Bloem Water head office. So it's the first building in the country that runs off hydropower, or can run solely off hydropower. And it should pay off in about 6 years. And the reason, this is quite a long period, the payback period. And the reason for this is because we've installed this large installation, 100 kilowatt, but we do not utilize it to its fullest. In the evenings, when at 4:30, when people go home, this plant, the demand drops to only about 25 kilowatts. And that stays like this for the next 16 hours or so, 15 hours, until the next morning, 8 o'clock, when people start arriving at work again. Over weekends, we also don't have the full demand. So we've got this installation that we had to design to cater for this maximum, but we do not utilize the full capacity of this. People then ask, can't you put this electricity back into the grid? Unfortunately, we can't. The controls is such, and the synchronous generator is such, that this is a standalone unit. So you can't switch between synchronizing it with a grid or doing it, have it as a mini grid. So it's always one or the other. So you can't switch between the two. So, but still, it is paying for itself. They're saving on electricity, and this was now a few years ago already. And we obviously, this was based on certain assumptions of how the electricity prices would increase over the next few years. This has also been shown to differ from our assumptions. With suddenly last year, we're having this 15% increase again, which makes all of these installations even a lot better for us. Just this is a learning exercise for all of us, and a very important element is that it needs commitment to utilize this facility to make it work. So initially, it wasn't operated as often as what I would have liked it to see operated. But once it started to be part of the key performance indicators, your KPIs of the board members or the managers at Bloem Water, then that starts to change the picture. Then there's a commitment to making sure that this plant actually runs, because we're saving 60,000 rand a month on electricity, for instance. So that's the commitment that's needed, and to make this a success. Initially, also, it was a manual process where you switched over between Centlec, which is the electricity supplier, and the hydro. But there were then times when the electricity demand in the building started to, especially in the winter time, exceed what we initially thought it would exceed, and went more than the 96 kilowatt that we can actually generate at this, which resulted in some voltage drops. So we then had to make some new plans, and that increased the cost of, that's why the cost for electricity or the control panels was a little bit higher in this installation. We then created some automatic changeover panels. So inside the Bloem Water head office, we looked at the distribution and all the panels that they've got in the building. And whenever there's more demand in the building than one can be supplied from the hydro, we basically switch back some of the areas of the building, we switch back to Centlec. So we supply hydro all the time, but as soon as certain parts, as soon as the demand outstrips what we can supply from the hydro, we don't switch back completely the whole building to Centlec. We only switch certain parts or certain areas of the office building, we switch back to Centlec. And that means we still maximize our utilization of the hydropower in this process. So more examples, City of Tshwane. Initially, we had a desktop study looking at some sites, and we saw, oh, there's 1.6 megawatts available. Then if you go into a bit more detail, you actually start recording flow, recording pressure, you realize that there's actually more potential than what you initially thought with our assumptions. So we went up to 2.4 megawatts. And now it's even a little bit higher with more data that we have. And that was just for a few of the sites. In the City of Tshwane, we have 260 pressure reducing installations. So that actually means potentially you've got that many sites that could be looked at. And now not all the sites are necessarily going to be viable. Some might be too far from the grid, or some might be the flows are too little to actually generate. And I'll get to that still in a few slides' time. So some of the installations that we did was, for instance, this installation at Anlin Reservoir. So inside existing, or inside, there was a new reservoir that was constructed, and also a new pressure reducing station. As part of that, they then also installed 3 50 kilowatt pumps as turbines. So 2 of the pumps actually, which is used as turbines, is connected to the grid, and one of them is supplying the electricity on the site, but more than what obviously is needed. But that's what we decided for in this specific installation. Another example would be the installation that's now planned at Heights High Level Reservoir. So here's a Google image of the CBD of Pretoria. Where I've just drawn the circle, the yellow circle, is where we have the Heights High Level Reservoir. And it's an important strategic reservoir because it supplies quite an important area in the city. Unfortunately, this pressure reducing station was vandalized. And although they had some guards at this reservoir site, eventually the roof was removed, the windows were removed, the spindles of the valves were cut off. So it needed to be repaired. So during this process of deciding on what to do, it was decided to build a new pressure reducing station a little bit further down the mountain towards Exaro's side in Valhalla. And it's a concrete structure. So no more tin roofs. It's a concrete sort of impenetrable structure. Vandalism proved to a certain extent. But when they decided, and we started looking at this pressure reducing station, we decided to already include the option and the space to add turbines at a later stage. So within the next few months, that pressure reducing station will be completed, and it will have all the pressure reducing valves in there for operating the distribution bulk supply to these reservoirs. We then, at now a later stage, will add 2 turbines, one for 265 kilowatt and the other for 455 kilowatt, and was minimal extra cost to just make this pressure reducing station chamber slightly bigger, but now it affords us the opportunity to add these turbines into that installation. You always need those pressure reducing valves, as I mentioned before. If you need to do maintenance on the turbines, then you need to switch back to the pressure reducing valves. Otherwise, you're not going to be able to supply water. Another example is Garsfontein Reservoir, where you go through the whole technical evaluation, you look at all the information that's available, you do the site evaluation, see if there's enough space, what will be the easiest way to access the site, how would you connect into it, where's the closest substation that you can maybe connect to, are you going to use the electricity on site, is there flow and pressure data available, and you come up with some design. So in this specific example at Garsfontein, we have 3 reservoirs. And on that little picture, you would see a little red box in between those reservoirs. That is the existing pressure reducing valve chamber or pressure reducing station. And the idea is that one could simply, with the red line coming in here from the bottom corner, it goes into this pressure reducing station. And then from there, it feeds into the 3 reservoirs. We could just upstream of that pressure reducing station, we could build a small little turbine room, 5 by 7 meters, and inside that turbine room, we then take the inflow and put it through the turbine and then feed into the downstream side of the pressure reducing valves, and that feeds directly into the reservoirs. So it's not a lot of civil works. It's a small building, a bit of pipe work, and the turbine. That in this way, you could then utilize the pressure that we have there, which is about 150 meters that we can dissipate, and we have about 70 megaliters a day that's supplied. And it supplies constantly, 24 hours a day, 365 days a year. We actually have the supply to this area or to these reservoirs. And yes, there is some variation between winter and summer, but that's not significant in these bulk reservoirs over here. And it also would be good if you have a nice constant steady supply to meet your supply meeting demand in terms of water supply, but that also provides us the opportunity to generate nicely almost 0.8 of a megawatt year. So looking at the cost of an installation like this, so it just shows you the financial sort of information on this, saying it will probably take 2 years to implement something like this, from starting to design it to building it. It's the capex cost we calculated by getting some quotations and what would the O&M cost be, what would the escalation be during the construction. So we incorporated all the different cost components, and it came to about 40 million rand for this project. So that would result in internal rate of return of about 26%, payback period of about 4.4 years, and the levelized cost of energy over the design life would only be about 31 cents. So this shows that it's definitely a viable scheme. So yes, there's a high initial capital outlay, capex that you need to supply to build this. And as I mentioned, the turbine being a very expensive cost component. But because you are generating 24 hours a day, 360 days a year, it results in very high IRRs and the levelized cost of energy becoming low. And we've played around the sensitivity analysis on exchange rates and whether or not if you do wheeling agreements. And so we looked at different scenarios and options, and what we escalate the energy cost by only 8%. Whereas if we get, for instance, another 15% increase, the internal rate of return actually goes up to 28.5%. Your payback period becomes even less, and the levelized cost of energy becomes less, because you are now increasing above what we assumed here we would be increasing by. There are still other benefits which you didn't include, like the Income Tax Act 1612B and carbon credits. So there's still other ways of still getting other benefits from this installation as well. We just purely looked at what it would cost to build this and how long it would take to pay for itself. And as I mentioned, the other benefits are still, other benefits for you. An example here in City of Tshwane, Salvokop, where water is supplied from Klapperkop Reservoir to Salvokop Reservoir. We did some work with the Danish Embassy and the City of Aarhus, who's got a mutual beneficial relationship with the City of Tshwane, and analyzed. And this is a picture inside a pressure reducing valve, inside the Salvokop Reservoir pressure reducing valve station. And where the stairs are, there is actually enough space for us to put the turbine in. So in this case, it becomes also a lucrative installation, because I do not have to build a new turbine room. I can just use the existing space that's available inside this pressure reducing valve chamber and add my turbines. So in this case, we can add a 152 kilowatt Francis type turbine, but a pipework turbine, and connecting it to the grid. The advantage of doing it in these municipal areas is, for instance, the City of Tshwane can add this generating capability into their own grid. So we're not connecting to the Eskom grid, we're feeding it into the City of Tshwane's own grid over here. And as I indicated in the bottom right corner, we show some efficiencies. So at 100% flow, this turbine is actually 87% efficient. So it's a smallish turbine, but it's very efficient. And even at 40% flow, so if you start reducing the flow, you're still going to get 70% efficient. So a Francis type turbine is efficient over a very wide range, which is a nice feature of it. Pumps as turbines do not have this feature. They become very inefficient very quickly if you start changing the flow rate. But if you start adding the generator to it, the overall efficiency is then reduced. So we're probably sitting with about 82, 81% efficiency for a smallish installation like this. As soon as I maybe go up to half a megawatt or a megawatt, I'll probably get it close to 85, 86% efficiency. We're not just looking at the existing technologies. We are also looking at developing some newer technologies and horses for courses, some smaller Pico type installations. So the picture on the right-hand side is a collaboration we did with WD Power, which is a turbine manufacturer in South Africa, and also operator of some turbine facilities, where this is called the Otter turbine, and water basically goes straight through the blue pipe you see there with the generator on the outside of it. And this is only a 9 kilowatt installation and installed in Doornkloof Reservoir in the City of Tshwane. And the idea behind this was to generate electricity for the telemetry system, the cathodic protection of the pipeline, the alarm system, the lights, and the guardhouse. So it's all used on site. So you can have a small installation, bypass around the pressure reducing valves. And this is a large chamber, so there was enough space in there and all we do is we're generating electricity for a specific need on site. The bottom picture shows some other types. We call them inline pressure wheels, a bit more of a robust type of installation, where we have this sort of wheel, which is similar to a pelton, but now it's a pressurized type of environment, so that you latch and attach to the top of the pipeline, with this wheel then sticking into the flow velocity of the water, and that turns a pulley through the axle, and we connected this to a conventional alternator, typically that you find in a car or a truck, and we have the pulley just to increase the velocity that we have, or the speed of that, for the alternator, and we can generate a kilowatt or two with this type of installation. So just trying to find ways of being able to generate electricity, small amounts, but for a specific purpose. So the question I had initially was, when does it become viable? Now, this smaller unit of generating a kilowatt or so is probably not going to be viable in the sense that you're going to pay back this in 4 or 5 years. But the subsequent benefits that you get from now on being able to generate electricity somewhere remotely inside a chamber, away from the grid, that nobody knows about almost, but you now have the control over your water supply system, is a huge benefit. So it's not the actual value of the electricity you're generating, but it is the power that you now can generate and utilize then on site specifically. Other examples, I'm not going to go into too much detail here, at wastewater treatment works, where you take the height difference from the outlet, where you have a nice constant flow through the wastewater treatment works, and you can maybe generate. So this is at Tseku Gat. We can generate up to 16 kilowatts there. You can add a siphon turbine here. We went for a type of Kaplan turbine. And again, you don't generate electricity to put it back into the grid. We generate electricity and put it back into the treatment facility itself. So it's after the meter. So again, the city of Tshwane will just purchase less electricity from this. But it also allows you for some hybrid opportunities where you can have solar and wind and a turbine on a specific site, especially if you have space available like you might have at some of the treatment facilities. This is one of my colleagues, Ms. Chantal Niebuhr, installing a hydrokinetic turbine in a canal system in the Northern Cape. Different type of application. And again, this was a hybrid system where we had solar panels, because the Northern Cape is ideal for that, linked with these kinetic type turbines that feeds into a water treatment facility. And the last example here was a recent one we just completed, was a rural electrification project where we did this at Tina Falls in the Eastern Cape, and supplying a Kwamadiba rural village. And there we take the water from the upstream side at the intake. We've got a head trace. We drilled a hole through the mountain, created a tunnel, the penstock, and then the turbine room at the bottom, and releasing the water through a tail race. But this was more sort of a conventional type. In this case, we again went for crossflow type turbine based on the head, and we went through the route of a modular type of approach where we installed this inside a container. So you can have a nice controlled environment where you build your whole turbine and fit it and install it, and then you just take the container to the site and connect it up with the pipe work. So just a different approach we then took. And this was only a 51 kilowatt type of installation we had here. So in conclusion, we've done a number of WRC projects and other consultancies projects where we looked at hydropower in general, but also in a lot of cases more specifically in Conduit hydropower. So there are a number of Water Research Commission reports available, guidelines on how to go about doing this. We've done a number of scoping studies, and we've done a number of research projects through the Department of Science and Innovation. And the purpose of all of these studies was to highlight and to show what can be done. And the city of Tshwane has now taken this step forward by already starting to implement a number of these. And they even gone so far as to take a mayoral committee decision or resolution that says whenever you design a new reservoir in the city of Tshwane, you have to look at maybe incorporating the opportunity to add hydropower to that. Doesn't mean you always have to do it. It just says at least consider it, look at it. The Department of Water and Sanitation gazetted a document on sustainable hydropower generation, a policy document. It was a few years ago now. Unfortunately, it hasn't progressed since then, where the opportunity to add some hydropower to dams and the outlets is being considered. As part of some of the research project we've done, we included in the general authorization process that if you have a small installation up to 300 kilowatts, a run-of-river scheme or a dam or a weir, you do not have to go through a full water use license application process. You can just have a general authorization, which is a lot easier, a lot simpler, just basically a risk assessment and informing the department of your installation. But you don't have to get the permissions and that you need with a water use license application, which can be cumbersome and quite expensive as well. So there are many small, mini, micro, pico options that can be considered. So as my last slide, my take-home message is that I believe that there are numerous hydropower opportunities in South Africa, especially utilizing existing infrastructure. And why we like to focus on those is because a lot of the capital has already been spent. You have this infrastructure, so just try and latch onto that, piggyback onto that, and add the turbine. As an example, the eThekwini municipality have more than 2,000 pressure-reducing valves. So in my mind, immediately I see 2,000 potential locations to install a turbine. You can even install it at your house, but you'll probably just generate enough electricity for charging a cell phone because you don't use as much water at your house. If you use it continuously, you'll be able to generate more. But then obviously you would use all of that water. So there are a number of hydropower plants which is considered to be low-hanging fruit, easy installations, quick installations. We know of a project in Eskom that can generate 10 megawatts, and it will pay off in 2.5 years. So there are opportunities out there that just need to be developed. We can do these installations without special subsidies. As I indicated, we didn't even include carbon credits or some of the other benefits, and we can still show that it's a viable installation. Going into a type of hybrid installation also makes sense. If you have an installation, but you need to upgrade the transmission line to tie into the grid, if you spend money doing that, why not just add maybe a solar system as well to that? In that case, you can even make it more worthwhile and to develop. We are at the moment busy compiling our Hydropower Atlas. We do know about the wind atlas and the biomass atlas and the solar atlas, but there's nothing like that for hydro. And that puts a bit of a damper on it, and people are not always aware of the opportunities that do exist. And when they set up the integrated resource plan, they only looked at the grants Inga scheme supplying hydropower electricity from the Democratic Republic of Congo, whereas we have a number of opportunities here in South Africa as well. So that is what I would like to share with you on Conduit hydropower. And if there are any questions, I'll gladly answer them. But maybe Kulakani, if we can first maybe also get some input from the panelists. So I'm going to just stop sharing my screen.
You know, Prof, I still like calling you Prof Marco. So you have to survive with the title. Thank you so much for the presentation. I think it was very informative, and it should have achieved and has achieved the objectives that you actually set out. We looked at the case studies, some of the theoretical outputs that inform the direction. So well done as well. Thank you so much for it. We do have some questions from the chat room. But before you go to them, I would like to welcome Jay, one of our panelists. He had indicated that he was going to be joining slightly late. He's from the Water Research Commission. So, Prof, there's a question from Doc, who was worried, Dr. Senamela, who was worried if there are any pressure losses that are caused by the system in the pipelines. Maybe if you can touch on that quickly.
Okay, so I mean, you want pressure losses. So I'm not adding a hydropower installation to a pumping line, for instance, because that means I'm adding pressure and then I'm taking it away again. So I'm installing it at locations where I sit with this excess pressure, which I would like to get rid of. And I could do that somewhere along the line as well. I don't have to do it right at the end. I could do it halfway along the line if that's a better location for me. But then I still need to allow that there's enough pressure downstream of my installation to still get the water to the end reservoir, to overcome the friction in the pipeline to get to the end reservoir. I can't have it take all the pressure away and then obviously it stops there. So the pressure loss is not a problem, but I control how much pressure loss I'm taking or how much pressure head I'm taking from the system. So that is all what I designed in the turbine to do, is to extract a certain amount of pressure from the system and for a specific flow rate that I guide through it.
Okay, thank you for that, Prof. Two questions from one of the panelists, Mr. Lushozi, if he can actually show his face as well as I go through his questions. He was wondering in Bloemwater, why isn't the electricity sold to the other clients that can actually use it to actually reduce the payback period, the companies that could be around there?
The reason for this is because of the type of turbine that we selected, or not the turbine, more the generator and the whole system. So our installation there is not grid connected. We have an isolated grid or islanded grid that feeds this one demand, and that demand is this Bloemwater head office, the building itself. If I grid connected this at that stage when we did this 5-6 years ago, we will still be busy trying to do it. Because it's cumbersome. I mean, there's no Centlec wouldn't have been able to assist us necessarily in that, and so we decided we are generating enough electricity on this with this plant, and we're going to use that just on site. So we're not grid tied at all, and we can't sell. There was no feed-in tariffs available at all at that stage. So that was our decision. So you either have to decide one or the other. Either I'm generating electricity for an islanded grid, or I'm generating electricity that I'm putting back into the grid. But then you obviously need to have that arrangement in place to say I'm feeding back into the grid, but sometimes also I'm using electricity on the site, for instance. So we at that stage decided on we're only generating for the site, but now that also means we've got electricity spare capacity. So we did look at other uses for it. So for instance, in the evenings, there's a road leading up, Msuzi Road, leading up to Bloemwater head office that's got a number of street lights. So we said, okay, why not take that part off the grid from the municipality, and Bloemwater supplies electricity to that set of street lights, just using the electricity a little bit better. Another one was we looked at data mining as well to say, can't we add some small little data center there or some Bitcoin data mining machines? And whenever we don't use the electricity that we're generating, let's put it into some other type of use. So there are other things to consider as well and to look at.
I'm gonna go to Lenesha's questions because she was wondering if there are potential storage options that could be considered in both CAPEX and OPEX for such instances. Are there any that you've come across, and which ones have you applied?
So storage options, obviously going for some battery type of storage. The problem is I'm generating, let's say in Bloemwater, I'm generating 50-60 kilowatts an hour too much electricity during for the whole weekend. So it's going to be quite a large storage, and then I'm not using that storage again because I'm not connecting to the grid. So we haven't looked at adding batteries, for instance, to this installation. The idea would have to be some pump storage schemes, but our installation is too small for that. But we haven't looked at other uses for that. If we went for a smaller installation, maybe a 40 kilowatt or so, then it might have been a way to say add 40 kilowatts only, use a 40 kilowatt installation, and during the weekends we generate more power and we put it into the batteries, and during the week then we use some of that power that we've stored over the weekend. So yes, we could have downscaled our turbine and then utilize or add storage to it as an option.
Okay. And then lastly, from Tunzi, he was wondering if there is easily available information to compare the different technologies with the associated capital investment requirements and their payback period. Do we have that easily packaged somewhere?
So as part of the Water Research Commission project, we did sort of compile a list of potential suppliers of the different technologies. So there's all the different turbines and different manufacturers that showed an interest in supplying to South Africa. We have that sort of summarized in those Water Research Commission projects. The cost, not as much. So you get sort of generic cost functions, but they vary. And unfortunately, in South Africa, they vary quite a lot because of exchange rates. And it's a huge capital investment and a huge part of the total cost. So it goes up and down quite a lot. I mean, we were just last year, we were at 19 Rand a euro. Now we're back to 17 Rand something a euro. So that adds to the uncertainty, unfortunately, in this type of installation. The rest of it, we work with about a ballpark figure I always work with is between 35 and 50 million Rand a megawatt. So that's the ballpark. But it's site specific. So if I do the Salvo installation where I already have a chamber, I'm probably going to be closer to the 35 million Rand a megawatt. If I have to do a lot of civil works and a pipeline and a big turbine room, it's probably going to be close to 50 million Rand a megawatt. And scaled from that. So if I have large turbines or megawatt turbines, then it's probably in that range. But if I go for a very small installation, that might change. So unfortunately, there's not a clear answer. If you think of the one we did a few years ago, it was 3.5 million Rand for the Bloem Water one. And that was about with 35 million Rand a megawatt, if you convert it now to a Rand per megawatt installation. The benefit comes in that you're generating 24-hour base load, 24 hours. So although it's a huge capital, you do pay it off quickly because of the generating of electricity for 24 hours a day. And then that starts adding up if you do it over 20 years, over 20-year period.
Thank you so much, Prof. Next, we're going to take the panelists that's coming from the biggest water institutions in the country. So if Zekuza could also come on the floor while I take the president's question. Dev?
Yes, I have maybe a question and to Marco in a different way and a comment. Firstly, it's been so many times I've heard this presentation, and every time I hear it, the passion that Marco exuberates is just marvelous to hear. You just keep on intriguing me, and I'm sure you intrigue others, especially now that we have load shedding, and you're giving a solution for a base load solution, which is fantastic. The concern I have is that we have these clever solutions, but we're seeing load shedding existing in the country. What do you think your challenges are to bring the solutions to fruition? Because it's still, let's call it virgin territory right now. And how do we drum support to government to say, oh, we've got great solutions here that is much more competitive to solar or wind, and it's got a big role to play to avert the crisis that we currently have at the moment. How do we get the message? And this is perhaps more than you, Marco, with the panelists as well, that we seem to navigate in a political landscape where logic and common sense should prevail no matter what, whether it's a business world, political landscape. And it's up to us, as the power lies with the people that experience this. Right now, the recession, we're coming through COVID, the people experience the pain. And now that the elections are coming close to us, how do we position ourselves to take these clever solutions to market?
Okay, maybe I'll just quickly, a few sentences and then I'll hand over to the panelists. I just saw in Cape Town how politically they drive the fact that they don't have load shedding, or they could reduce the load shedding because they've got the pump storage scheme in Cape Town. And the same could be done here to say, there's benefits on of developing these sites, because you'll have a distribution of mini installations and small installations that would feed and be able to take off the load and eventually reduce the need for certain areas to be load shared. You will not get to 1,000 megawatts that you can do the whole all of the country or support the whole country, but you can add to less areas needing to be load shared, for instance. So you're absolutely right, Devin, that it is there's a higher level that need to make decisions on this. The hope is that once some of the bigger water utilities develop some of these installations a larger scale, that will stimulate the market more and drive and showcase what can be done. We don't have to. It's not pilot plant level anymore. We've developed now, and we can show it's running and it's working. I think it's now just to scale it up in more areas and to show those benefits that we can get from it.
Thank you so much, Prof. Really appreciate it. The next segment is looking at the two panelists. One is representing Rainwater, the biggest water board probably in Africa, and bids lots in Europe and overseas. The other one is Joburg Water. So both of them are driving the innovation opportunities in the institutions. One of the questions that we had for both, so I'll start with Rainwater, is Rainwater considering any hydropower projects as an energy mix option? The same question will go up to you, Dr. Kuzwa, but starting with Mr. Lishos.
Okay, thank you, Chair, and thank you, colleagues. Yes, definitely at Rainwater, we are looking at implementation of hydropower across our network. Given the amount of the huge network that we have, I think it's just a no-brainer, especially given what Prof has presented. We are definitely looking at it. Thank you.
Thank you. We're looking forward to seeing it in the market. Dr. Kuzwayo?
Yes, sir. From a Joburg Water point of view, we actually have tried an installation of this sort through an expression of interest a couple of years back. Unfortunately, that didn't go to market as there were a couple of glitches in the process. But I have been tasked with reinstalling that process via the innovation space in Joburg Water, where the idea is, of course, again, to go to market with a different scoping. And also looking at our internal processes, because one of the ideas I'm trying to drive is having, especially with with load shedding around, is to ensure that we can sustain our wastewater treatment plants. And one of the aspects which I'm looking into sort of pushing in the next year or two is to having off-grid systems, especially using hydropower as a means of running of the different plants that we have, because we have 6 of them, which run extensively on what you call electricity. We also do have biogas plants, but those, of course, we're still trying to get to a point of optimizing them. But definitely the idea is to go there, and there is efforts that we're already looking into from a Joburg Water point of view.
Okay, and what financing models are both the institutions considering as you take them out to the market? Are you going to finance them yourselves, or are you looking at a concession type of structures? What's the current thinking?
Well, from Rainwater's side, given the fact that such decisions are made at a capital investment level, which is a very high level within the organization, we haven't gone there yet. So on that note, I wouldn't say that we have made, from business point of view, a decision in terms of now how it is going to be financed. But on a ground level, there is various options that has been looked at, which are going to be recommended to the principals. For instance, we did look at partnering with other institutions such as DBSA, to mention just a few. And then also the option of financing it ourselves. It's one of the prominent options, which also we are considering. Also, given the fact that it's a public knowledge that the former minister, Minister Sisulu, congratulated Randwater in them attaining the green bond. Well, it goes without saying that that could be one of the options, because I mean, such bonds, they come with such initiatives. So then the long and short is to say, at the moment, the business has not made that decision, but those are the options that we have at our disposal. Thank you.
Maybe as a follow-up before Dr. Kuzwa, you come on board, you indicated self-financing. Does the institution have the capacity to finance itself?
Well, it's difficult to say yes or no, but from my point of view, I think, well, the institution does have the capacity, but obviously such decisions are made at a level of CFO, considering a lot of other things. I mean, just looking at the public financials, one could conclude that the business does have such muscle, but you find that when the experts in terms of finance look at it, then maybe they come up with a different point of view than the one that I have.
Okay, thank you so much.
But this is definitely an option that is on the table.
Okay, thank you so much, Mr. Lishozi. Dr. Kuzwayo, what financing models, and does the institution have the capacity to finance?
Well, Water is a subsidiary of the City of Johannesburg. And of course, the city does have a capital investment sort of plan going forward. As I indicated, that there was an installation that was done a couple of years back, where the idea was to use the city's capital investment to try and, of course, to work this into its plans. And of course, I'm thinking of going forward, there'll be the same, we'll be using the same kind of front, where, of course, from the wastewater treatment plant's perspective, as I indicated, we'll be using the in-house finances. Of course, we do have those because they'll be more of a smaller scale. Then, of course, when you look at the bigger picture, then, of course, we'll have to go via the city itself. Hope that answers your question.
Okay, so what I'm getting is we do have money to finance them as well, but it still needs to go to capital investment. And then lastly, okay, Doc?
Yeah, we do. Like I said, it's already in the works. So we've already sort of worked out all the sort of the dots and the particles out of it. So it is something that's going forward, and the money will be availed through, of course, the city itself, with our current engagement agreements with between the two subsidiary and sort of the big boys. And from our side, from an innovation point of view, that will have to come via our budget. And of course, we do have a budget for that. Of course, the idea is also sort of go from a proof of concept, pilot scale, all the way to a feasibility investment in terms of now rolling it out across all the plants if possible.
Okay. Lastly, do you believe the institutions have the capacity to be able to take this project out to the market and be able to manage them? Mr. Lishozi?
Even though we have never managed a hydropower installation, but if you look at what Prof has presented, hydropower is nothing more than, if you look at, I mean, Randwater has a lot of huge pumps, and by definition, if you look at the pump, I mean, the pump utilizes energy to create a water flow. And then now, if you look at hydropower, it's more of a reverse, where hydropower uses water flow to create energy. So one would argue there to say there are synergies there. And then now looking at the expertise that we have, especially from assets such as pumps and other assets, and generally management of a huge projects that we have been engaged on as Randwater, and the success thereof, and also considering the fact that hydropower will also follow the same life cycle in terms of project management in like any other project that we have managed. So in that aspect, then I would say we do have the capacity to manage such projects, project management, engineering, or otherwise.
Yeah, thank you, Mr. Lishozi. Dr. Kuzwayo?
Yes, just to piggyback on Mr. Lushaw's answer. We have a similar setup in that we have a lot of dedicated project managers. We have many units which look at different aspects of the company itself from an operational point of view. And it's quite robust and it has a lot of skills that are diverse and able to deal with this. Where, of course, we have the engineering services unit. We've got the program management unit, as well as all the supporting structures. So in a nutshell, this wouldn't be hard. And also in line with what Mr. Lushozi has said, we do sort of have those infrastructures in place where we can actually play with this to a point where I'm sure success is one of the, won't really be an issue.
Okay, no, great to hear. While I note Mr. Lushozi's comments, I'm going to ask Jay to come to the floor. In your comments, Mr. Lushozi, you are indicating an opportunity from what you have picked up from the keynote speaker of other opportunities to deal with CP and telemetry across the network. That can only indicate we should be seeing more and more of hydropower projects that should be coming out of rainwater. From both institutions, we look forward to your activation of the market and driving the market participation. Jay, from your side, from a research point of view, research is always critical in driving the market and informing the market. Do you believe that in the country we've done enough research to be able to educate on hydropower and the opportunities for us to drive the market forward?
Well, you know, from our contribution to date, I think we've prepared sufficient knowledge to prepare the sector to have a catalytic effect. Because, like I said, all the tools, the guidelines, you know, if tomorrow somebody says, let's enable this, we will be able to train the court and, you know, the kind of artisans to start taking this forward. What Marco, you know, did not mention that this area of focus was conceptualized by WRC in its foresight, you know, from several different angles. Okay, one was it was a response to the load shedding aspect. It was in response to the green pathway. Okay, but it was also response to opening up water to a circular economy. Okay, so if you look at those three elements, they start, you know, responding to our own local challenges around job creation, around enterprise development, around localization as the components that can stimulate a whole industrial pathway. So what Marco presented, and we shouldn't only get fixated on the big stuff. I mean, the big stuff is great. It's going to, you know, have its own character and challenges, like Marco said, because all that energy needs to be parked somewhere. So we have to open up pathways onto the grid so that, you know, we create this relationship between the big generators, you know, but then there's the small generators, okay? And every small generator is going to be an enterprise, a local enterprise, whether it's a community, whether it's a small artisan, etc. And all of them are going to have an opportunity to contribute to this economy and sustainability. So this is how we vision this pathway of stimulating an industrial platform for hydropower in South Africa. You know, and like I said, that we have a good history of the normal runoff river schemes and dams, etc. The interesting low-hanging fruit started coming in the sense of the conduit, and that's what the term we use around conduit hydropower is saying that we can harness excess energy while we supply water. You know, and it wasn't attractive in the past because, you know, the whole energy industry was subsidized through coal and etc. So you know, it was subsidized to such a level that it was driving the economic pathways in the apartheid areas. Okay, and I think that, you know, we inherited that problem, that suddenly everything started to become expensive because the reality hit. Okay, the maintenance of the plant was not today's problem; it was historic. It was building up. So all these consequences have come to put the energy sector under pressure. And what we're saying that in the mix, we're not saying that, the hydro is the only way to go. We're saying that in the energy mix, hydro has a potential, but there's many barriers to come over. I mean, the Water Services Act is very specific that as a water service authority, you can't produce energy and sell energy. But we can test that because, there's no law, but we should go ahead in the absence of law and be pioneers and start doing stuff, not be held back by something that, it's not interpreting. So
No, it's
opening
true.
up that, that's the first thing. The second thing is that most of the time people like to do big projects, and big installations. The juice is on the smaller stuff, okay? The decentralized options, etc. So it's working out the logistics and the business model as municipalities, because you own the infrastructure. You can't just give it to any private sector. So how you create this, what you would call energy right through the system that opens up the market and creates all this partnership is where you have to focus on in terms, because you're going to need a lot of capacity. I've seen somebody talk about, what about all the theft and the stuff? The theft and the stuff is a current problem we're having, okay? Because, we've never foreseen that this would be a problem. It doesn't happen in China because they shoot you first. They got all the guys with a gun ready to shoot. We haven't reached that point. I mean, I don't think we'll reach that point, but I'm saying that this platform organizes for us, to use the energy to put in sensors to drive this, to put the cables on the pipes so people don't steal it, etc. It's got a vast opportunity. So that's why we say that, there's a circular economy waiting to be exploited, and we need the transition.
Yeah, I think on that point, Jay, I see we're also starting to run out of time. I've come across a lot of information on your website in terms of the Water Research Commission that speaks to hydropower. Is that the right platform to direct everyone to go if they want to read more on the Water Research Commission website?
Yes, and just keep a tab on our events and etc. Because getting via email, sometimes people forget, but just looking at some of the daily updates, etc. We'll run a course now and again. We'll run training on certain things and new products, etc. So it just keeps you abreast. We are there to take any questions and support. Like I said, we the facilitator, we the glue of the sector. So we work with the Rand Waters, the Joburg Waters, the Marcos, etc. And we create this glue that brings this knowledge together to make it happen. And I think that's what we do.
No, to my panelists and everybody who attended, thank you so much for this platform, for all of us to come and share information. IDC did apologize, but we'll share the financing information to everybody that actually attended. It was truly a good session and very informative. It works out better, Prof, when someone is presenting the information when you're reading yourself. It's always educational. Truly grateful to the panelists and everybody who attended. Thank you so much. Please have a wonderful day further.
Thank you.
Thank you. Cheers, everyone.
Thank you, sir.
Thank you.
Thank you.
Thank you, everyone.
Thank you.